I'm Vaidehi Srinivas. I'm a student at Northwestern University, and today I'll be telling you about some new tools we've developed for smooth analysis. More precisely, I'll be telling you how to prove least singular value bounds for random matrices with dependent entries. And this is joint work with Aditya Bhaskara, who's at the University of Utah, Eric Everett, who is a postdoc at Northwestern and is now starting as faculty at the University of Florida, and Arvindan Vijayaraghavan at Northwestern University, who's also my advisor. So the object we're going to be dealing with in this work are perturbed matrices. So consider a set of underlying base variables, x1 through xn, and we're going to look at a matrix where each entry of this matrix is a low-degree polynomial in these entries of x. And the way we're going to draw this random matrix is we're going to draw values for each of these variables independently. So each xi is going to be some vi, which is an arbitrary value, but then it's going to be perturbed by some small random perturbation. So here you can think of this as some small Gaussian random variable that's being added, where the magnitude of this variable is rho. What we'd like to say is that a random matrix that's drawn this way is robustly full rank with high probability. And the way we quantify that kind of statement is by arguing about the least singular value of this matrix. And we'd like to say that that is at least polynomially sized in the size of the input and in rho, which is the magnitude of the perturbation. The challenge with proving statements like this is that the entries of M are highly dependent random variables. And so we need to somehow argue about the action of this matrix despite the fact that these entries are very dependent. Statements of this flavor fall into a category called matrix anti-concentration bounds. So to talk about let's start by talking about just what is concentration versus anti-concentration. So for a one-dimensional random variable, a concentration bound tells you something like there's this large window and my random variable will fall within this large window with high probability. Anti-concentration tells you the opposite, that for any fixed small window, my random variable is unlikely to fall exactly within that window. If I were to draw a random Gaussian variable, it's unlikely that it'll be exactly 1. So the analogs of these kinds of statements to matrices look something like this. A matrix concentration bound will tell you that the action of a random matrix M is unlikely to be too far away from the zero matrix. We quantified this by looking at the maximum singular value of this random matrix M and showing that it's within a polynomial of 0 with high probability. Matrix anti-concentration tells you that the action of a random matrix M is unlikely to be too close to any fixed matrix M prime. So we would quantify this by looking at the least singular value of M minus M prime and showing that it's large with high probability. And this tells us that in every direction, M is acting significantly differently than M prime does. So our contributions in this work are giving two new approaches for proving these anti-concentration or least singular value bound for these structured random matrices. And so one of our approaches is a new hierarchical net construction that's suited to proving anti-concentration bounds. And the second one is an inductive argument to analyze smooth modal contractions of an arbitrary tensor. Unfortunately, I don't have time to talk about these techniques in this version of the talk, but I refer you to our paper for more details. These two approaches let us prove new results for random matrices with dependent columns, and they also let us recover alternate proofs of known results for some sorts of structured random matrices. And once we have these bounds on least singular values for random matrices, this allows us to resolve conjectured smooth analysis bounds for a variety of algorithms and problems, including subspace clustering, which I'll tell you a little bit about, and computing linear sections of varieties and power sum decompositions of polynomials that I won't have time to touch on this talk. So what is smooth analysis exactly? Smooth analysis is a paradigm of analyzing algorithms. So typically we study algorithms under the paradigm of worst case analysis, where we analyze the runtime or the performance of an algorithm on an adversarially chosen instance. So for example, here, if we have this map of instances, the instance space to runtime, we would choose the worst possible instance and analyze the runtime of the algorithm on that instance. This can be very pessimistic, especially when the algorithm does well, except in a few pathological cases. One way to get around this is to look at average case analysis, where we analyze the performance of an algorithm on an instance that's drawn from a fixed distribution. So here, for example, if we take the uniform distribution over all of these instances, then maybe the average runtime will come out to be something like this. The problem with average case analysis is that sometimes it can be too tailored to a particular distribution. And it's not clear that if that distributional assumption fails, that our resulting guarantee actually translates to other settings. So somewhere in between the best of both worlds of these two paradigms is smooth analysis, where we analyze the runtime of an algorithm on a perturbed instance. So you can think of this as you choose some arbitrary instance, perhaps adversarially, but then you analyze the runtime of the algorithm on a small perturbation of that instance, some other instance that's chosen randomly within a small ball of this adversarial instance. And this is the perturbed instance. And then we'll consider the runtime of the algorithm on this instance. So essentially, getting a smooth analysis bound tells you that if there's a good smooth analysis bound, that there might be pathological instances, but they're somewhat isolated in the instance space, and that most instances are well behaved. Another way of thinking about this is that in a small ball around any instance, most instances are still well behaved. So to give a concrete example of what we're looking at, let's consider the problem of subspace clustering. So in subspace clustering, our input is defined with respect to a collection of S hidden subspaces, W1 through Ws, where each of these hidden subspaces is a t-dimensional subspace within an ambient space of dimension n. And then we see a set of points A, where there's a hidden partition of A into these subsets A1 through As, where each subset AI is drawn from points within the subspace Wi. Now we're going to make two assumptions about this to fit this into the framework of smooth analysis. One, is that the subspaces that we see are themselves somewhat perturbed. So they might have been adversarially chosen, but then some small amount of randomness was added to each of them to make them slightly random. The second is that the set of points that we see that's drawn from each of these subspaces might again have been adversarially chosen. Perhaps all of the points A in A1 were chosen to be the same point, but then each of them had some small independent randomness added to them, some small perturbation that kept them within the subspace. And we see these slight perturbations of this adversarial point. Now, given this input, our goal is to, given A, recover these subspaces W1 through Ws. So for example, here if we see these points A, then our goal is to recover these subspaces W1 through Ws, perhaps like this. And one algorithm for this problem in this setting is given by this framework of robust vector space decomposition that was developed in this nice line of work by Chandra Garg, Kayal, Mittal, and Saha. And essentially, it works when these subspaces are mutually linearly independent. That means that for any vector that's in one of the subspaces, you can't write it as a linear combination of vectors from the other subspaces. And this really fits well with the smooth analysis model. Because these subspaces were perturbed to begin with, we should expect that they should be linearly independent. Except this immediately fails if the number of subspaces times the dimension of each subspace, that's S times T, is greater than the N, which is the ambient dimension of the space. Then we just run out of dimensions for this to even be possible, for these to be mutually linearly independent. But this doesn't really point to some sort of information theoretic hardness about this problem. For example, if we had a third subspace in this picture, we should still expect this problem to be solvable. So, okay, does this mean that this approach is just doomed, or is there some way to fix it? And it turns out there actually is this kind of slick way to fix this, which is we're going to take the points in A that we were given, and instead of just treating them as points A, we're going to look at this A tensor D times. So the way you should think about this is A is some vector, and we're going to take the outer product of this vector with itself D times. That's going to give us a D-th order tensor. And then we're going to flatten that up to symmetry. That's what's happening. But essentially, we're not adding any new information. We're not adding any new randomness here. We're just taking the information that is in A and we're multiplying it with itself a bunch of times. So how does this help us? Well, it turns out that if A was in a subspace Wi, then we have that A tensor D times is going to be in the subspace of Wi tensor D times. And this A is going to live in an approximately n to the D dimensional space, ambient space. But this subspace that was originally T-dimensional to begin with, when we tensor it up D times, is going to be a T to the D-ish dimensional subspace of this n to the D-ish dimensional ambient space. So now we can choose D so that S times T to the D is less than N to the D. And since T to the D grows much slower than N to the D, we should be able to choose a D that this works for. So now we'd like to just apply robust vector space decomposition to this new set of points, this the A tensor D times, that's defined with respect to these hidden subspaces, which is the Wi tensor D times. But remember, we need that these subspaces are mutually linearly independent for this algorithm to work. So it's not clear that these Wi's tensor D times should have the same kind of randomness property. So we know that this will work as long as these tensored subspaces look kind of random. So what does it mean for these subspaces to look kind of random? So first, let's define precisely what we mean by the tensored subspace. So subspace V tensor D times is going to be the span of all of the vectors that are within D tensor D times, as I described previously. We're going to call this the symmetric lift of the subspace V. And it turns out that if V is an m-dimensional subspace of Rn, then V to D is an m plus D minus 1 choose D dimensional subspace of Rn plus D minus 1 choose D. So these binomial coefficients are coming in because this is essentially living in some sort of symmetric space, and so this is the dimension of the symmetric space. But you can essentially think of this as being like m to the D and n to the D. So what is the randomness property that we want to capture? Well, we'd like to say that, imagine we fixed an arbitrary low-dimensional subspace S. And then we were to draw a completely random low-dimensional subspace U, then it's unlikely to non-trivially intersect S. These two subspaces have to intersect at 0, but it's very unlikely that U is going to land exactly on top of S. We'd like to say that this is true even for a perturbed structured low-dimensional subspace, which would be like V tilde, which is a perturbed subspace, tensor D times. We'd like to say that this kind of subspace is also unlikely to non-trivially intersect some fixed S. Now, the interesting thing about a statement like this is that a random low-dimensional subspace in an n to the d-ish dimensional space is going to have m to the d times n to the d degrees of randomness, approximately. Whereas this structured low-dimensional subspace that I'm describing, all of the randomness is within V tilde, which is just an m times n dimensional space. And so this only has m times n degrees of randomness. So we'd like to say that this object that has much less randomness than a fully random object still behaves approximately like a fully random object. And that's why we describe this as being pseudo-random. So now I'd like to give you one sample theorem that we're able to prove using our new techniques that we develop in this work for symmetric lifts. So let phi be a projection matrix of rank delta times n plus d minus 1 choose d for some fixed delta greater than 0, where recall that n plus d minus 1 choose d is the dimension of the ambient space, and you can think of this as being essentially n to the d. And so this means the delta tells us that this phi is rank deficient in the ambient space, but it's within a constant factor of being full rank. Then we're going to consider U tilde to be a perturbed n by m matrix. Then as long as m is less than a constant factor less than n, we have that the least singular value of phi times this U tilde tensor d times is at least a polynomial in rho and 1 over n, with probability that has an inverse exponential failure probability. So one way to interpret this statement is it's saying that this U tilde tensor D times is very unlikely to non-trivially intersect the kernel of phi. But remember that phi was an arbitrary projection matrix. So the kernel of phi is an arbitrary subspace. So this lines up with the definition that I gave you on the previous slide. Another way to interpret this kind of statement is to say that phi is likely invertible over this U tilde tensor D times. So phi is not invertible over the ambient space. It's rank deficient, we know that. But over this low dimensional subspace, we should expect that it actually is invertible. And this actually ends up having nice algorithmic implications that we explore more in this work. So one interesting thing about this statement is that previous work focuses on random matrices where the columns have independent randomness. Whereas this, when you write out U tilde tensor D times as a matrix, the columns of this matrix will have lots of dependencies on each other and on the columns of U tilde precisely. And so this gets around this kind of roadblock that was there in previous works. So coming back to the application I told you earlier of subspace clustering, we were looking at this problem where we wanted to recover these subspaces given these points that were get from the subspaces in a smooth analysis setting. And we had this algorithm due to Chandra, Garkayal, Mittal, and Saha called robust vector space decomposition that works when these subspaces are mutually linearly independent. And they had conjectured that this should give a smooth analysis guarantee, but the thing that was missing was arguing that these tensored subspaces are going to look somewhat random. And this is the kind of statement that we are able to fill in to show that the algorithm that they present for subspace clustering does indeed admit a smooth analysis guarantee. So in conclusion, our work makes progress on understanding anti-concentration properties of perturbed matrices with dependent columns. And another way of thinking about this is that anti-concentration properties are essentially least singular value bounds on these random matrices. And our results imply new smooth analysis guarantees for a variety of algorithms for which previously smooth analysis guarantees were either left open or were conjectured, including subspace clustering, which I told you a bit about, and computing linear sections of varieties and power sum decompositions of polynomials that I didn't have time to touch on in this talk. So if there might be other applications in which you would need to prove that a perturbed structured matrix M has random-like properties, and our techniques might be able to help in these cases. Thank you so much for listening. Please feel free to reach out or look at our paper for more details. Thank you.